Good day, everyone. Welcome to the first part of our discussion on nuclear chemistry. For this lesson, I will be describing with you the makeup of the nucleus. So this is where nuclear power comes from. Also, I will be describing the criteria for nuclear stability and calculate the mass deficiency in nuclear bonding. Let me define what nuclear chemistry is. It is a subfield of chemistry dealing with radioactivity, nuclear processes, and nuclear properties. What's the difference between nuclear reactions and chemical reactions? So chemical reactions are what we have studied before. So for chemical reactions, no new elements are formed. Only the electrons participate in bond breaking and bond formation. Relatively small amounts of energy is released or absorbed during chemical reactions, and that is what we calculated in thermochemistry. The rate of reaction depends on factors such as concentration, temperature, catalyst, and pressure. On the other hand, in nuclear reactions, elements may be converted from one to another. So new elements are formed in the reaction. Particles within the nucleus are involved. Tremendous amount of energy are released or absorbed during nuclear reactions. And the rate of reaction is not influenced by external factors such as concentration, temperature, catalyst, and pressure. So let's have a brief review of an atom. You are quite familiar with the particles that are present in an atom, such as the proton. The proton can be found in the nucleus. And it has a charge equal to +1. And its mass is approximately equal to 1 atomic mass unit. The neutron can also be found in the nucleus. It has no charge at all, and it is slightly heavier than the proton. So the electron is flying around the nucleus, okay? So you have the example. So this is a representation of an atom. The nucleus is there, and the electrons are flying around the nucleus. It has a charge of -1, and the mass is very, very small. 1/1840 atomic mass units. So the nucleus is composed of nucleons. We call the protons and the neutrons as nucleons. A nucleus is characterized by two numbers. A, is the total number of nucleons in it. So that means to say the sum of the number of protons and neutrons. And the atomic number Z represents the number of neutrons. So we can represent the mass number and the atomic number in a symbol that is like this. So what is this symbol all about? So we call this the Nuclide symbol. So in the Nuclide symbol, we represent it by the element symbol and then the mass number. And then the atomic number is the number at the bottom. So the mass number is the bigger number or the larger number because it represents all the residents of the nucleus. So knowing the nuclide representation, we can identify and determine the number of particles that are present in the nucleus. Let's say, for example, for aluminum 2713, the total number of nucleons is 27, and the total number of protons is equal to 13. So the neutrons is equal to 27 minus 13, so that's the larger number minus the smaller number represents the number of neutrons. So for a neutral particle such as an atom, the number of protons is equal to the number of neutrons. So we can also determine that in this kind of a representation. A representation like this also is a symbol for an isotope of an element. The nucleus contains most of the mass of the atom, so it has a very small volume. One chemistry textbook author described the atom as, if we compare it to a large baseball field, the entire atom is very large, while the nucleus may be compared to the ball of the baseball. So it is very, very small. The radius is approximately 10 to the minus 15 of a meter. The number of protons determines the identity of the atom. So the atomic number represents the number of protons, and it serves as the ID number of an element. The number of neutrons in an element can vary. So a particular element can have atoms of different neutrons. They have the same number of protons, but they have different number of neutrons, and we refer to them as isotopes. The average atomic mass is the weighted average of the masses of all naturally occurring isotopes. So the atomic mass that you find in the periodic table is actually the average mass of all the naturally occurring isotopes of an element. Let's say, for example, boron, how atomic mass is determined. Let's consider boron here contains two types of isotopes, naturally occurring isotopes. So it is B10 and B11. Look at this representation here of the nuclide. The atomic number is not placed at the bottom here because we can always look up the atomic number in the periodic table. So boron 3, 10, and 3, and boron 11. So the isotope can be represented in terms of the mass number actually. So boron 10 and boron 11 are naturally occurring isotopes of boron. Boron 10 weighs 10.0129 atomic mass units, while boron 11 weighs 11.0093 atomic mass units. So boron 10 is only 19.91% in the universe. So a large percentage of all the boron atoms in the universe is actually boron 11. So it is the greater contributor to the atomic mass of the element boron. So if you are asked to calculate the atomic mass of boron, then it is the summation of the isotopic percentage multiplied by the isotopic mass. So these masses are referred to as isotopic mass, and these are the abundance, isotopic abundance. So the mass fraction of each one of them is considered. So the abundance of boron 11 is 80.09%. So for boron 11, 80.09% is 0.809 multiplied by 11.0093, so that's 8.817 atomic mass units, while for boron 10, that would be 19.91% of 10.0129, and the relative or average atomic mass of boron is this one. Okay, so this is not part of our lesson. I just am describing the importance of the different isotopes of an element. So these are examples of some of the elements having isotopes. So hydrogen has 3 naturally occurring isotopes, stable isotopes. So protium is the most stable and the most abundant isotope of hydrogen. It has a mass number that is equal to 1 and an atomic number that is equal to 1. By the way, all of them have atomic masses equal to 1, atomic numbers equal to 1. The deuterium is heavy hydrogen. It has a proton and a neutron in its nucleus. So, the representation is 2, 1, hydrogen 2, 1. And tritium is the isotope of hydrogen that contains 2 neutrons in the nucleus, and this is the radioactive one. So the representation is hydrogen 3, 1. So another kind of element, carbon, has several isotopes as well. So carbon 611 is rare. It's not very abundant. The most stable is carbon 612, and this is most of the carbon that is present in all the carbon-containing compounds around us. So carbon 613 is still a stable isotope despite having one more neutron as compared to carbon 612. Carbon 614 is radioactive carbon. So this one is the one that is determined in radiocarbon dating, determining the age of artifacts. Carbon 15-6 and carbon 16-6 are unstable as well. When we say an isotope is unstable, it means it is radioactive. Isotopes may also be represented this way. So these are all correct representations of isotopes. So whenever you encounter problems about uh, representing daughter isotopes or parent isotopes in nuclear reactions, make sure that you have this information with them. So the mass number is very important. So that's the first part of our lesson. I hope you understand why there are isotopes that are unstable and radioactive. So thank you for watching. Well, let's now go to the next lesson.